Look around you. Everything seems to move, everything seems to turn. The Earth spins on its axis, making day and night. The planets orbit the sun, rotating as they travel. Stars whirl in distant galaxies, and entire galaxies spin around invisible centers. Even the tiniest particles, electrons and quarks, have a property called spin. Spin is everywhere, from the largest cosmic structures to the smallest components of matter. But why? Why does the universe have such a persistent tendency to twist and rotate? To understand this, we need to talk about a principle called angular momentum. You may have seen it in a simple experiment, a spinning top or a figure skater. When the skater pulls her arms in, she spins faster. When a top spins, it resists falling over. Angular momentum is nature's way of conserving motion. Once something begins to spin, it wants to keep spinning. It cannot simply stop without some force acting on it. This is not a rule invented by humans. It is a fundamental principle of the universe. Spin is not just a curiosity, it is a form of balance. Imagine a bicycle wheel suspended in the air. If you try to tilt it while it spins, it resists, twisting in response. That resistance comes from the same principle that keeps planets stable in their orbits and stars in their rotations. Spin is a kind of memory of motion, a way for nature to maintain consistency. The universe remembers how things move, and angular momentum is its bookkeeping system. Now consider something even more fascinating. Spin occurs at vastly different scales, yet the same principle applies everywhere. A galaxy made up of billions of stars rotates as a coherent system. A planet made up of countless particles and gases spins steadily on its axis. Even an electron, a particle so small it has no size in the classical sense, possesses spin. At first, it seems strange. How can something so small have a spin similar to a top or a planet? Here we enter the world of quantum mechanics, where spin becomes a fundamental property, not necessarily a literal rotation, but a type of intrinsic angular momentum built into the fabric of reality. Spin connects the everyday world with the extraordinary. When you see a hurricane, a whirlpool, or water swirling down a drain, you are observing the same principle in action. Nature favors rotation because it is an efficient way to manage motion and energy. Tiny imperfections, small nudges in a system, get amplified into large rotations. A slightly moving cloud of gas in space will collapse under gravity, and as it collapses, its tiny random motions increase, producing the spin of planets and stars. What begins as a subtle motion can become cosmic in scale. The remarkable thing is that spin is a universal language. From spinning electrons to spinning galaxies, the same rules govern the motion. It is as if the universe at every scale has a habit of twirling, conserving motion and preserving balance. Spin is everywhere because angular momentum is everywhere. Understanding this principle is our first step into a deeper mystery, the question of why the universe seems predisposed to spin at all. It is a mystery that invites curiosity, challenges our intuition, and connects the very small with the incomprehensibly large, reminding us that the cosmos operates with a surprising elegance and consistency. Now that we see spin everywhere, the next question is even more intriguing. Where did all this spinning actually begin? Planets, stars, and galaxies did not start out already twirling like tops. They had to acquire that motion somehow, and to understand it, we need to think about how objects form in the universe. Everything begins in clouds, vast clouds of gas and dust floating in space. These clouds are enormous, sometimes hundreds of times the size of our solar system. To the naked eye, they may look still, calm, and silent, but they are far from motionless. Tiny random motions ripple through the cloud, gas molecules bump into each other, pockets of dust drift, and energy from nearby stars stirs the material. These motions are so subtle that they might seem insignificant, yet they are enough to set the entire system in motion. It is the same principle you see when you give a barely noticeable twist to a slowly spinning wheel. The twist can eventually dominate the motion if the conditions are right. Gravity then enters the picture. This invisible force pulls the gas and dust inward, gathering material to form stars, planets, and other celestial bodies. As the cloud collapses, something remarkable happens. those tiny random motions are amplified. Imagine a figure skater spinning slowly with arms extended. As she pulls her arms inward, her rotation speeds up. The same principle applies to collapsing clouds. The more the cloud contracts, the faster it spins. What began as a nearly imperceptible drift turns into the rotation of an entire planet or star. Spin is not created from nothing. It is a conserved property of motion, amplified by the universe's own organizing processes. As the cloud contracts and spins faster, structures begin to form within it. Dense regions coalesce into stars, while the remaining material flattens into disks around them. From these spinning disks, planets form, each inheriting part of the original motion of the cloud. This is why almost all planets in our solar system spin in roughly the same direction around the Sun. It is a cosmic fingerprint of the original cloud's motion, preserved through billions of years. Even tiny deviations in the cloud's initial motions can lead to slight differences in planetary rotation. But the overall pattern remains. What is fascinating is how this process connects the microscopic with the macroscopic. At the smallest scales, particles in the cloud collide and interact in ways dictated by quantum mechanics. These interactions, although tiny, collectively contribute to the macroscopic spin we observe. It is a reminder that the universe is not chaotic. There is an underlying order, a way in which energy and motion are transferred across scales. Spin becomes the universe's signature, its way of maintaining consistency while allowing creativity in the formation of stars, planets, and galaxies. Spin also explains why the universe is full of patterns. Hurricanes on Earth, accretion disks around black holes, and the spiral arms of galaxies all originate from the same fundamental principle. Tiny initial motions, conserved and amplified by natural forces, become magnificent rotations that shape the cosmos. It is a story of emergency small, random beginnings growing into grand, ordered structures. Spin is not merely motion. It is the universe organizing itself, translating microscopic chaos into cosmic dance. In understanding this process, we glimpse the bridge between randomness and order, between the subtle nudges of particles and the majestic rotations of celestial giants. So far, we've talked about spin in planets, stars, and galaxies, but spin is not only a cosmic phenomenon, it exists at the tiniest scales in the particles that make up everything around us. Electrons, protons, and neutrons all possess spin. Quarks, which are smaller than protons, have spin too. At first, it is difficult to imagine how something so small can spin like a top. After all, electrons do not have physical size in the classical sense. They are not little balls you can watch twirl. Yet, they have a property called intrinsic spin, and this property behaves in ways remarkably similar to classical rotation. Quantum spin is fundamentally different from the spinning we see in the macroscopic world. You cannot point to an axis and say the electron is turning around it. Instead, spin is a built-in characteristic like mass or electric charge. It is a number that tells us how the particle interacts with magnetic fields and how it combines with other particles. For example, electrons in an atom follow rules. Based on their spin, two electrons cannot occupy the same state if they have the same spin. This simple principle, known as the Pauli exclusion principle, shapes the structure of matter itself. Without spin, chemistry as we know it would not exist. There would be no atoms with stable electrons, no molecules, and no life. Spin is not just a quantum quirk. It also connects to macroscopic phenomena. When a magnetic field is applied to a material, the tiny spins of electrons align, creating magnetism. The collective behavior of trillions of quantum spins gives rise to the magnetic forces that power motors, electronics, and even the compasses that guided explorers across the globe. The way a microscopic property scales up to affect the everyday world is a beautiful demonstration of the universe's interconnectedness. Spin at the smallest level influences the largest scales, shaping the material world and ultimately the environment we inhabit. There is something deeply mysterious about quantum spin. Even physicists struggle to fully visualize it. Unlike planets or tops, electrons are not spinning in space in a literal sense, yet the mathematics of spin predicts their behavior perfectly. It can be measured, manipulated, and used in technology, but the question remains, why does spin exist at all? Why is this property embedded in the fundamental fabric of reality? Spin is both a law and a mystery. It is something the universe simply includes in its design, a feature that seems necessary for matter energy and motion to interact coherently. Spin also demonstrates the unity of nature. From the tiniest particle to the largest galaxy, angular momentum governs motion. Electrons have quantized spin values, planets have conserved rotational motion, and galaxies rotate around invisible centers of mass. The principle is the same across scales, showing a remarkable universality. Nature does not distinguish between the very small and the very large when it comes to rotation. The rules are consistent. In a way, spin is the universe's signature, a thread connecting quantum mechanics to cosmology, chaos to order, randomness to pattern. When we study quantum spin, we are peering into the universe's blueprint. It tells us that rotation is more than motion. It is an organizing principle, a fundamental code written into reality itself. Everything spins not just because it moves, but because the universe preserves balance, symmetry, and order in motion. Spin is both a property and a process, a microscopic instruction set that scales up to shape stars, planets, and galaxies. Understanding it is not just about science. It is a window into the deep logic of the cosmos, a reminder that even the smallest, invisible aspects of reality have profound effects on everything we see and experience. Despite all that we know about spin, it remains one of the most puzzling aspects of the universe. Even with the most advanced telescopes, particle accelerators, and mathematical tools, humans still struggle to fully explain why everything spins. The difficulty lies not in a lack of observation, but in the limits of our intuition. Our minds evolved to understand the world at a human scale, tables, trees, birds, and rivers. We are comfortable with objects we can see, touch, and manipulate. Spin, however, operates on scales both far larger and far smaller than our everyday experience. Galaxies rotate in ways that take millions of years to complete, while electrons spin in ways that cannot be visualized as a literal turning motion. It stretches the imagination. One reason we struggle is that we instinctively try to picture spin as a simple rotation, like a spinning top or a turning wheel. But in quantum mechanics, spin is not literally a rotation. Electrons and quarks have intrinsic spin, a fundamental property that obeys the rules of mathematics, yet defies our attempts at physical visualization. Even the cleverest diagrams and models are only metaphors, not reality. When we measure spin, we observe its effects, such as magnetic alignment or energy levels, but we never see the electron physically spinning. This mismatch between our mental models and reality challenges our ability to understand spin intuitively. At cosmic scales, spin presents a different kind of challenge. Galaxies, stars, and planets follow angular momentum conservation, but the initial conditions that cause them to spin are often chaotic and complex. Tiny random motions in a primordial cloud of gas can amplify over millions of years into the organized rotation of a star or planet. Predicting the precise outcome requires understanding not only gravity and motion, but also turbulence, friction, collisions, and countless other factors. Even small variations in the early cloud can dramatically change the final rotation. Spin is deterministic in principle, yet incredibly sensitive to initial conditions, making it difficult for humans to fully comprehend or predict. Spin also forces us to confront the limits of our knowledge. It is one of those phenomena that reminds us that science does not always answer the why questions. We can explain how spin works, measure its effects, and apply its principles to technology and astronomy. But why the universe includes spin as a fundamental property, why it appears universally at every scale, and why it follows the precise rules it does, these remain mysteries. It challenges us to separate observation from understanding, to accept that nature has habits and principles that exist independently of human reasoning. In a way, struggling to understand spin is a reflection of the broader challenge of science. The universe is not obligated to conform to our intuitions or mental shortcuts. Spin stretches from the microscopic to the cosmic, connecting electrons to planets, atoms to galaxies. It is simple in principle. Motion is conserved, but profoundly complex in its manifestation. Recognizing this allows us to appreciate the elegance of nature. The universe is not random chaos, nor is it simple. Spin is a bridge between order and complexity, between what we can measure and what we can imagine. Studying spin teaches patience, humility, and curiosity, reminding us that the cosmos is more subtle, more interconnected, and more extraordinary than we often realize. One of the most effective ways to understand spin is through thought experiments, because spin is often counterintuitive and cannot always be seen directly. Imagine, for instance, a perfectly round, frictionless cloud of gas floating in space. At first, it seems motionless, serene, and silent. Yet even in this cloud, molecules jostle and drift, and tiny, random movements exist. These motions may seem insignificant, almost invisible, but they are enough to initiate a rotation. Gravity then begins to pull the cloud inward, and as the cloud collapses, something remarkable happens. The initial tiny motions are amplified. The more the cloud contracts, the faster it spins, just like a figure skater pulling her arms inward. What was once a subtle, almost imperceptible drift becomes the spin of an entire star or planet. Now imagine forming planets from the leftover material of this spinning cloud. Dust grains collide, stick together, and gradually grow into larger bodies. Each new body inherits part of the cloud's original rotation. This is why the planets in our solar system mostly spin in the same direction around the sun, and why they have their own rotations. Even slight variations in the cloud's initial motions create differences in planetary spins, yet the overall pattern persists. It is as if the universe leaves its fingerprint on everything it creates, encoding spin into the very structure of matter. Spin can also be explored at the microscopic level. Consider electrons in a magnetic field. Each electron has intrinsic spin, a property that behaves mathematically as if it were a tiny magnet. When exposed to a magnetic field, electrons align their spins in specific ways. Even though we cannot see an electron physically spinning, we can measure its magnetic influence and predict how it will behave. Now imagine billions of electrons aligning their spins collectively in a material. This alignment creates the magnets that we use in technology, from compasses to electric motors. Here, a microscopic property scales up to produce macroscopic effects, showing that spin is not confined to abstract mathematics. It shapes the physical world we interact with daily. Spin also explains the natural patterns we see everywhere. Hurricanes, whirlpools, and spiral galaxies all emerge from the same principle. Tiny initial motions, conserved and amplified by the forces of nature, grow into organized rotations that span vast scales. Even a simple swirling pattern in water obeys the same laws as a galaxy spinning over billions of years. These thought experiments reveal a profound truth. Spin is a universal language, a way the universe organizes energy and motion. From the smallest particle to the largest celestial object, the rules are consistent, elegant, and deeply connected. Spin is both simple and mysterious. It follows clear mathematical principles, yet challenges our imagination. By exploring thought experiments, we begin to grasp how tiny motions become cosmic rotations, how invisible quantum properties shape the visible world, and how the same principle connects phenomena separated by immense scales. Spin is more than motion. It is the thread that weaves the universe together, linking chaos to order, randomness to pattern, and the microscopic to the cosmic. It is the universe speaking in a language of rotation, inviting us to observe, measure, and wonder. Even after centuries of study, spin remains one of the most fascinating and elusive aspects of the universe. There is much we understand, but there is also much that remains mysterious. On the one hand, we know the laws that govern spin are consistent, measurable, and remarkably reliable. Angular momentum is conserved. A spinning object will continue to spin unless acted upon by an external force. Planets, stars, and galaxies all obey this principle, as do particles at the quantum level. Tiny random motions in gas clouds can be amplified to produce the majestic rotations of celestial bodies. Electrons and other particles follow precise rules about their intrinsic spin, which determines how they interact with magnetic fields and with one another. These are concrete, testable facts that reveal the incredible regularity of nature. Yet even with this knowledge, many questions remain unanswered. Why does the universe seem predisposed to spinning at every scale? Why do quantum particles possess intrinsic spin in the first place? Why do these rules appear universally, from the tiniest electron to the largest spiral galaxy? These are questions for which science has no final answers, at least not yet. Spin appears to be built into the very fabric of reality, a property that exists simply because the universe allows it. It is not something we can deduce from more fundamental principles. It is a foundational feature of nature itself. Part of the challenge in understanding spin comes from its universality. It manifests in ways that are both familiar and counterintuitive. At macroscopic scales, we can visualize spinning planets, whirling hurricanes, or rotating tops. At microscopic scales, however, spin behaves in ways that defy everyday intuition. Electrons do not spin like tiny spheres. Their rotation is an intrinsic quantum property. Yet the mathematics of spin allows us to predict their behavior with astonishing accuracy. We can manipulate it, measure it, and apply it in technology, but truly grasping what spins remains beyond our intuition. Spin also reminds us of the limits of human knowledge. Science can describe how spin behaves and even manipulate its consequences, but the why often eludes us. We can trace the chain from tiny particle motions to the rotation of planets and galaxies, but the reason the universe adopted spin as a fundamental feature is still a mystery. It is a reminder that nature is not obliged to conform to human logic or intuition. The cosmos operates on principles that may be simple in mathematics yet profound in implications, challenging our imagination at every turn. Despite these mysteries, the study of spin offers profound insight into the universe's underlying unity. The same principles govern phenomena across scales. Quantum particles, stars, planets, and galaxies all follow the rules of angular momentum and rotation. Spin links the microscopic and the cosmic, revealing a deep coherence in the laws of nature. By observing spin, we glimpse the patterns that connect energy, motion, and structure across the universe. It teaches us that order emerges from randomness, that tiny initial motions can shape colossal outcomes, and that the rules of nature are elegant, consistent, and interconnected. Ultimately, spin is more than a physical property. It is a language of the universe. It expresses balance, symmetry, and conservation, and it connects the visible with the invisible, the ordinary with the extraordinary. Understanding what we know, while acknowledging what we do not, allows us to appreciate the universe not merely as a collection of objects in motion, but as a vast, interconnected system governed by principles that are at once simple and mysterious. Spin, in all its forms, is a window into the cosmos, revealing both the elegance of physical law and the enduring wonder of reality itself. When we step back and look at the universe through the lens of spin, something extraordinary emerges. Everywhere we look, from the smallest particles to the largest galaxies, motion manifests as rotation. This is not coincidence or accident. It is a pattern woven into the very structure of reality. Spin connects the microcosm to the macrocosm. The same principles that dictate how an electron behaves also guide the paths of planets, the rotation of stars, and the majestic spirals of galaxies. In this sense, spin is not just a physical property, it is a universal language, a thread that unites all scales of existence. The more we understand spin, the more it reveals the elegance and subtlety of the cosmos. Tiny nudges in a cloud of gas billions of years ago grew into the rotations of planets and stars. The invisible spin of electrons shapes the stability of atoms and molecules, making chemistry, biology, and life itself possible. A hurricane swirling across the Earth, a whirlpool forming in water, and a galaxy twisting in the void of space all reflect the same underlying principles. Spin is not just motion, it is the universe expressing balance, conservation, and symmetry. Spin also reshapes the way we see our place in the cosmos. Every object, from the chair you sit on to the stars above, is part of this ongoing dance of motion and rotation. The universe, does not separate the very small from the very large. It applies the same rules across scales. Angular momentum, intrinsic spin, conservation laws, they are not limited to the laboratory or the telescope. They are written into the blueprint of reality, operating whether we observe them or not. Recognizing this forces us to reconsider our assumptions about simplicity, complexity, and the unity of nature. There is a philosophical lesson hidden in the physics of spin. Nature preserves motion, amplifies small beginnings, and organizes chaos into structure. Random fluctuations can lead to predictable outcomes. Chaos and order coexist, and what seems like randomness at one scale becomes organized motion at another. Spin demonstrates that the universe is neither arbitrary nor purely mechanical. It is elegant, coherent, and astonishingly interconnected. Understanding it requires humility, patience, and a willingness to accept that some aspects of reality may forever challenge our intuition. In a way, observing spin is like reading the signature of the cosmos. It is a reminder that the universe is not static. It is alive with motion, energy, and structure. From the invisible twirling of electrons to the sweeping rotations of galaxies, the universe is a cosmic dance. Each rotation carries the memory of motion, the imprint of forces acting over billions of years, and the subtle interplay of chance and necessity. Spin teaches us that motion is not merely a physical phenomenon. It is a statement about the organization of reality itself. When you next watch a spinning top, gaze at the night sky, or consider the invisible world of atoms. Remember that you are witnessing a principle that unites all things. Spin is more than physics. It is a lens through which we can see the universe as both simple and profound, orderly yet mysterious. It invites curiosity, inspires wonder, and reminds us that reality is richer than our imagination. To understand spin is to glimpse the hidden patterns of existence, to see the universe not as a collection of objects, but as an intricate, rotating, interconnected whole. Spin is the rhythm of reality, the heartbeat of the cosmos, and the eternal dance that links everything everywhere, all at once.